Welcome to the second video on areas. Let's start off with a beautiful quote by French mathematician Sophie Germain. Algebra is nothing more than geometry in words. Geometry is nothing more than algebra in pictures. And as you've seen from the previous video, there's a beautiful interplay between algebra and geometry. Now, before we can do some Olympiad problems, let's have a couple of weapons or theorems to help us out with the problems we're going to see soon. So the first area theorem that we're going to look at is the area of a parallelogram. And you may know that in this diagram, the area of this parallelogram is base times height. So base times vertical height. But do you know how to prove it? Again, there are several ways to prove this, but here is my way of proving it. So I'm going to start off by labeling some points. So I'm going to label this point A, label this point B, label this point C, and from point C I'm going to drop a perpendicular up until this point D. Let's label this point E, and let's label this point F. Alrighty, so you can clearly see that triangle ABF is congruent to triangle ECD. So you can pick up triangle ABF and you can drop it onto triangle ECD. So these two triangles have the same area. So let's say the area of triangle ABF is X. Therefore, because triangle ABF and ECD is congruent, the area of triangle ECD is also X. And let's say the area of quadrilateral BCYF is Y. I am going to notate it like this. So BCEF is equal to Y. So whenever you see the square brackets, you look at that polygon and the area of that polygon in this case is Y. So square brackets BCEF means the area of quadrilateral BCEF is Y. And I will use this notation quite often in this video. So please make a note of that. Great. So let's have a look at our diagram. So parallelogram ABCE in terms of these variables will be triangle ABF and quadrilateral BFEC, and clearly you can see that is X plus Y. Now have a look at quadrilateral BCDF. So quadrilateral BCDF can be broken up into quadrilateral BCEF and triangle CDE, and that is also then Y plus X. And so we see that therefore that the area of parallelogram ABCE is the same as the area of quadrilateral BCDF. And have you noticed what kind of quadrilateral BCDF is? Yes, it is a rectangle. And the distance from F to D is clearly by the diagram DF is equal to B and CD is H. And the area of a rectangle is base times height, so it's BH. And there you go. Here you have a short proof of why the area of a parallelogram is base times height. So remember, every rectangle is a parallelogram, but not every parallelogram is a rectangle. And here we have our first theorem, our first weapon for the problems that we are going to tackle in this video, is the formula for the area of a parallelogram. Now let's look at another area formula, and another important shape that sometimes you encounter is a trapezium. So a trapezium is a quadrilateral where you have two opposite sides being parallel. So in this diagram, the sides notated by A and B, they are parallel. And in this trapezium, let's call the vertical height H. It can be shown, and we will show shortly, that the area of this trapezium is a half H times A plus B. So adding up the two opposite sides, halving it, multiplying it with the vertical height. Again, There are several ways you can prove that the area of this trapezium is given by this formula, but I am going to do it in the following manner. So I am going to redraw my trapezium over here, and I am going to drop a perpendicular height over here, so we know that's h, and I'm going to drop a perpendicular height over here, so that's going to be h again, and let's call that distance a. Let's call this distance t. Let's call this distance a, because in the middle you have a rectangle, and in the rectangle opposite sides are equal, and let's call this distance s. Great. And so the area will be the triangle plus the rectangle plus the area of the triangle on the right. Okay, let's do the maths. The area of a triangle we know is a half t times h. The area of the rectangle in terms of these variables will be a times h, and the area of the triangle on the right will be a half s times h. And you can see we can take out a common factor of a half h, and if we do that we left with t. Here you got to be careful. If I take out h and I take out a half, I'm left with 2a. Why? Because a half times 2 will be the 1, and then you're left with a times h, which you meant to be left with. And then finally, in the last term, if I take out a half h, I'm left with s. Alrighty. And now this can be rewritten in the following manner. I can rewrite t plus 2a plus s as a plus t plus a plus s, because a plus a gives me 2a. Now looking at the diagram, we want these two trapeziums. It's not drawn to scale, but we want the two trapeziums to be that the length of the bottom should be b. So looking at the diagram, we see that b must be t plus a plus s. So filling it into this expression, we have t plus a plus s will give me b. And we have now derived this formula, y, the area of a trapezium, is a half vertical height times the sum of the two parallel sides. And here we have the area of a trapezium. Now, it's a useful formula, and there are occasions in Olympiad problems where you have to play with trapeziums. But a very important remark is the following, is that every parallelogram is a trapezium. Okay, there are trapeziums which is not a parallelogram, but every parallelogram is a trapezium. So we can actually use theorem 2 to prove theorem 1. So using theorem 2, we can actually use it to prove theorem 1. So if you have a parallelogram that looks like this, and let's call that B, and let's call that B, and we say that those two sides are parallel because it's a parallelogram. And let's call the vertical height h. Then we can say that the area of this parallelogram, using the theorem for the area of a trapezium, should be the following. It's a half h, adding up the two parallel sides. So we're using the two parallel sides, b plus b. So now let's do the math. So it's a half h, b plus b gives me 2b. And what is a half h times 2b? Yeah, it's b times h, giving us theorem 1 again. So if you have established the theorem of a trapezium, you can also use that to prove that the area of a parallelogram is base times vertical height, because every parallelogram is a trapezium. So very, very, very cool. Alrighty, and now the third theorem or weapon that we are going to need for the problems in this video is a theorem about the cevian of a triangle. So what is the cevian? A cevian is defined as a line that intersects both a triangle's vertex and also the side that is opposite to that vertex. So in this diagram, we have triangle ABC. AD is a cevian of triangle ABC. Why? Because A CV is a line that intersects both a triangle's vertex. So in this case, AD passes through vertex A and is also the side that is opposite to that vertex. So you see that point D is on line segment BC. So it satisfies the definition of a CV. Now, in this case, you can see that the CV AD divides a triangle into two parts, the triangle on the left and the triangle on the right. And we can ask ourselves, can we come up with a relationship of the ratio of the two triangles in terms of sum of the side lengths here? And it turns out, yes, we can. And this is theorem 3 for today's lesson. It says the following, that the area of triangle ADD divided by the area of triangle ADC is BD divided by DC. So the CV divides the triangle into two parts, and the ratio of the two triangles is precisely how point D divides line segment BC. And the proof is actually very easy. So to do the proof, I am going to notate the vertical height H of triangle ABD with base BD, and H will also be the vertical height of triangle ADC with base DC. So you see that H plays a double role. It plays a role of being a vertical height for both of these triangles. And now let's do the calculation. So let's start off by looking at the area of triangle ABD. Remember, if I use square brackets, I am representing the area of that polygon. So we want the area of triangle ABD over the area of triangle ADC. And as I've mentioned here, we are going to use a base BD and we're going to use the base DC. So we are using the same vertical height. So the area of triangle ABD will be a half base BD times vertical height H. And the area of triangle ADC will be a half base, I'm using the base DC times its vertical height H. And we see some magic happening. The half at the top cancels with the half at the bottom. The H at the top cancels with the H at the bottom. And what remains is BD divided by DC. And there we have the third theorem or weapon for today's lesson. That the area of triangle ABD divided by the area of triangle ADC is BD divided by DC. And you will see some problems where this theorem is quite useful. Great. So I hope you have the three theorems written down. The area of a parallelogram, the area of a trapezium, and how a CV divides the area of a triangle. These are the three theorems that we will be using in solving today's problems. As a friendly reminder, the problems are coming from Professor Pillai's book that you can order from SAMO, titled 1000 Mathematics Olympiad Problems. As always, I hope you have pen and paper and you pause the video, try it out yourself before watching my solution. Maybe you have a more beautiful or elegant way of solving the problem. Alright, so the first problem we're going to tackle goes as follows. In the diagram, ABCD is a rectangle. Our job is to calculate the area of rectangle EGF. Alright, so we have some data, so we can already start filling in things. We know that AD is 6, so that means that BC is 6. We know that DF is 5, so by symmetry BE would be 5. And we know that AE must be the same as CF, and that's equal to 8 units. Okay, now let's see what else we can do. Our job is to calculate the area of rectangle EGFH. Now, as you know, in an Olympiad problem, you sometimes have to do sub-calculations, okay? So let's see if we can calculate the area of parallelogram DEBF. Now, there are two ways you can calculate the area of parallelogram DEBF. The one way you can do this, you can take the big rectangle, so you can go ABCD, and you can subtract the two triangles AED minus BCF. Okay, let's do this maths and see what we get. So the area of rectangle ABCD CD. That will be base times height, so that will be 13 times 6, minus the area of triangle AED, which is a half 6 times 8, minus the area of triangle BCF, which is also a half 6 times 8. Now 13 times 6, I'm going to leave it like that. And here a half 6 times 8 minus a half 6 times 8, we're left with 6 times 8. And now, instead of doing 13 times 6 minus 6 times 8, I'm going to take out a common factor of 6. What remains is 13 minus 8. And we know 13 minus 8 is 5. So this is 6 times 5. And it works out to be 30. Now there's an alternative way you could have worked out the area of parallelogram DEBF. If you decide to use the base DF, then you need the appropriate vertical height. And can you see in the diagram what is the vertical height if you're using base DF? Yes, you can see it, it's BC. So an alternative way would be it's DF times BC using theorem 1. So that's 5 times 6, which is also equal to 30. Excellent. So there are more than one way you could have established that the area of parallelogram DEBF is 30. Okay, now we can also use an alternative base. We can use the alternative base, which is BF. So if I'm using BF as a base, what will be the vertical height? Remember, EGFH is a parallelogram. So that means that if I'm using the base BF, the vertical height would be FG. Now, do we have BF at the moment? No. However, remember that triangle BCF is a right angled triangle, and we know two of the sides, and we know that angle BCF is 90 degrees. And whenever you see 90 degrees, you should be thinking maybe I can use Pythagoras. And because BC is 6 and CF is 8, I'm going to leave it for you to verify that using Pythagoras you can confirm that BF is equal to 10 units. So the area of the parallelogram is also 10 times FG, and we know that the area of parallelogram DEBF is 30. Therefore, we know that FG has got to be 30 divided by 10. You don't need a calculator for this. The answer is 3. So we know that GF is 3 units. And again, now if you focus on triangle DGF, you know two of the sides. You know the hypotenuse DF, which is 5 units. You know that GF is 3 units. So using the theorem of Pythagoras, you can establish, I'm leaving that calculation for you, that DG is going to be 4 units using Pythagoras in triangle DGF. So we know that DG is 4 units. And remember, BF is the same as DE, and they're all equal to 10. That means that if DE is 10 units and DG is 4 units, doing a little bit of accounting, we see that GE must be 6 units. So GE must be 6 units. And now we are ready to calculate the area of polygon EGFH. EGFH is a parallelogram, so we know that the area is going to be GF times GE, and we just calculated GF to be 3 and GE to be 6. 3 times 6 is going to be 18, and that is the answer to this problem. So maybe more than one way to solve this problem. However, when the dust settles, you will get an answer of 18. A nice little starter problem. Good. All right, let's move on to problem 2. Now, in this figure, PQRS is a parallelogram. T is a point on Q such that the ratio PT to TQ is 2 to 1. PU is drawn parallel to TR. What is the ratio of the area of PTRS to the area of PQRS? And you can see why this notation is so useful, because you can just tell yourself, I'm looking for square brackets PTRS divided by square brackets PQRS, if you know that square brackets represents the area of the polygon. Now, just like the quote by Sophie Germain, we are going to need variables to help us out here. Okay, so the first thing that we know is that the ratio from PT to TQ is 2 to 1. So if I decide to make TQ x units, I know that PT has got to be 2x units, because 2x divided by x will be 2, and that's meant to be what the ratio of PT over TQ is. Great. So introducing variables will help us to make progress in this problem. Now, we are told that PQRS is a parallelogram, and we also are told that PU is parallel to TR. So therefore, PT is parallel to UR, TR is parallel to PU, so PTRU is a parallelogram. And because it's a parallelogram, we know that if PT is 2x units, then UR has got to be 2x units. And we know that PQ is 3x units, and so therefore SR has got to be 3x units, so therefore SU is going to be x units. Great, we're making progress. And we know if we're dealing with parallelograms or trapeziums, we want the vertical height. So in this case, let's fill in the vertical height. Let's call that h. So in a paragraph, I will tell myself, or the marker, that I'm calling the vertical height h as indicated in this diagram, not drawn to scale. And by making TQ x units, we get PT SU and UR in terms of x. And now let's see if we can use theorem 1 and 2 to work out the areas of these polygons. Okay, so PTRS is a trapezium. And do we have a formula for the area of a trapezium? Yes, remember that was theorem 2. Scroll back to the start of the lesson. So PTRS is a parallelogram, and so it's a trapezium, so we can use the formula for the area of a trapezium. So it's a half h adding up the two parallel sides. So the one parallel side is PT, which is 2x, and the other parallel side is SR, which is 3x. Great. And now let's do PQRS. PQRS is a parallelogram. So we got to use the area of a parallelogram, which is base. So using the base SR, which is 3x, times its vertical height, which is h. And so what remains is the following calculation. So we have to do the h at the top cancels with the h at the bottom. And so we are left with a half 2x times 2x plus 3x, which is a half times 5x over 3x. If you want to, we can rewrite this as a half times 5x over 3x. You can see the x at the top cancels with the x at the bottom. And how do you multiply fractions? You multiply numerators and denominators. So 1 times 5 is 5. 2 times 3 is 6. And that is the answer to this problem. It is 5 over 6. So this is a nice problem because we get to use variables and the area of a parallelogram and the area of a trapezium, as mentioned earlier. Good. I hope you agree with that. Let's move on to problem 3. Problem 3 is a tricky little problem. First, let's read the problem. In this interesting diagram, D is a point on side AB of triangle ABC. E is a point on CD. And F is a point on CE. The areas of triangle AED, AEC, BFT and BFC are 6, 10, 17, 7 respectively. So the same order that they label the triangles is the order that they label the areas as indicated in this diagram. And our job is to calculate the area of triangle BEF. So pause this and see if you can try it out. If you get stuck, listen a little bit and then see if you can finish it off yourself. Okay, now one way we can solve this problem is to say, okay, let the area of triangle BEF equal to x, because that is what I'm looking for. Now, knowing that we're calling the area of triangle BEF x, it makes sense to say, okay, let's connect B to E. And if I'm calling that x, and knowing that the area of triangle DBF has got to be 17, using a little bit of area counting, that means that the area of triangle DBF has got to be 17 minus x. A little bit of area accounting. Okay, now we need to do something more. Now in this diagram, we see lots of triangles. But importantly, what you also see is a lot of covariance. And what does covariance make you think of? Yes, Theorem 3. Theorem 3 tells you that covariance help us to relate areas to side lengths. So we got to be careful in relating the correct areas to the correct side lengths. Okay, so there are a couple of things that we can do here, but if we are focusing on point E, you can see that point E is connecting point D to E, and it's connecting point E to C. So you can see that if we are smart, we can actually calculate DE over EC in two ways. One way is to say that AE is a covariant of triangle ADC. So that means that DE over EC is equivalent of triangle ADE over triangle AEC. Likewise, BE is a covariant of triangle BDC. So DE over EC is therefore the same as the area of triangle BDE all over the area of triangle BEC. Do we know the area of triangle ADE? Yep, it's given as 6. Do we know the area of triangle AEC? Yep, it's given as 10. Do we know the area of triangle BDE? Yep, it's 17 minus x. Do we know the area of triangle BEC? Yes, it's the area of triangle BEF plus the area of triangle BFC, which is x plus 7. So now what we have to do is solve for x to make these two fractions equal. So we cross multiply. So we get 6 times x plus 7 is equal to 10 times 17 minus x. Expanding the brackets, we get 6x plus 42. That's equal to 140 minus 10x. Taking the 10x to the left, we get 16x is equal to 170 minus 42, which works out to be 128. So therefore, x is 128 divided by 16. One way to divide by 16 is to half, 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 half. So by halving 4 times, you will see that 128 divided by 16 gives you 8. And so the answer to this problem is that the area of triangle BEF is going to be 8 units. And there you go. So a lovely little problem where we get to use the covariant problem. However, let me quickly share a second way of solving this problem. Again, using the covariant theorem. So I'm just going to erase. And this time around, I'm going to use different variables. Okay, so what I'm going to do is, just as before, I'm going to connect B to E, and this time around I'm going to call the area of triangle BDE as K, and therefore the area of triangle BEF is going to be 17 minus K. So my second solution is a change of variables, and I'm going to call the area of triangle BDE as K. Great. So And this way, how I'm going to solve this problem is by focusing on the following. I am going to focus on DE being a cvian of triangle AEB, or looking at DC as cvians. All right, so using the cvian theorem, I know that AD divided by DB can be calculated in the following ways. So first of all, it can be calculated as the area of triangle ADE over the area of triangle BDE. So DE is a cvian of triangle AEB. So the ratio of the triangle ADE over BED will give me AD divided by DB. In a similar fashion, I can also say that DC is a cvian of triangle ABC. So AD divided by DB will be the area of triangle ACD divided by the area of triangle BDC. Now, ADE, it's given as 6. I've called the area of triangle BDE as K. ACD would be adding up ADE and AEC, so that's 6 plus 10, and that's 16. BDC would be the area of BDF, which is given as 17, and BFC, getting tongue twisted here, as 24. All right, and so what we have is the following. That 6 over K must be 16 over 24. So doing the maths, we see that 6 times 24 is equal to K times 16. So K is going to be 6 times 24 over 16. And again, if you are a little bit lazy, you can split up 6 as 3 times 2, and you can split up 24 as 8 times 3 all over 16. And we know that 2 times 8 is the same as 16, so K evaluates to 9. So the answer that we're looking for, which is the area of triangle BEF, will be, in terms of these variables, 17 minus K, which is 17 minus 9, which is also equal to 8. So many ways of skinning this cat. So however you go about solving this problem, you will see here that the area of triangle BEF in this diagram evaluates to 8 units. A nice little problem which can be solved in many ways, as this diagram has many cvians and many triangles. Good. Alrighty. Trust you agree with that answer. Let's have a look at problem 4 on our agenda. In the following diagram, you have 5 squares labeled A, B, C, D, E. They are drawn along a straight line, each touching the next square at a vertex, as shown in the diagram. Square B has an area of 20. So we know that B has an area of 20. C has a side length of 4 units. So we know that C has a side length of 4 units. Square D has double the area of B. Already processing data, if B has an area of 20, we know that D has an area of 40. And this Olympiad problem wants us to determine the area of square E. Alright, so let's do some mathematics. So we know that the area of D is 40. So side squared will be 40. So each side of square D will be the square root of 40 units. Okay, and now let's draw a little diagram. Just parts of this a little bit bigger. So I'm not going to draw the entire thing. So here I have C. We know that that's 4 units. We know that that's 4 units. And now I have D over here. So this is square C and this is square D, and I know that this is square root 40 units, and I know this is square root 40 units, and then I have square E over here. So redrawing part of the geometry problem that could be useful is a good strategy. All right, and now we know that they're all drawn along a straight line, so we have a lots of 90 degrees lurking over here. Now, when you think of 90 degrees in a triangle, you should be thinking it's a right angle triangle, which means we can be using the theorem of Pythagoras. So let's call this distance x. So using the theorem of Pythagoras in this triangle over here, we know that 4 squared plus x squared will be root 40 squared. Now let's do the maths. 4 squared is 16 plus x squared is root 40 squared, means root 40 times root 40. Root 40 times root 40 is 40. So we see that x squared will be 40 minus 16. So x squared will be 24, or x will be root 24. Wonderful. So we know that x is root 24. Does this really help us? Well, inspecting this diagram a little bit closely, remember D is a square. So tell yourself that all of those angles is 90 degrees. More importantly, what you should also be telling yourself is that all the sides of a square are equal, and I'm notating it by these little lines. Okay, now looking at this a little bit even more closely, if we call this angle alpha, we know that the angles of a straight line adds up to 180. So if that's alpha and that's 90, doing the accounting, that's got to be 90 minus alpha. And if that's 90 minus alpha and then that's 90, that angle's got to be alpha. Likewise, if that's 90 and that's alpha, that angle's got to be 90 minus alpha. So what you see is the following, is that these triangles MNO and OPQ have the same angles and they have the same hypotenuse. So bearing that in mind, you can see that in essence that these two triangles are congruent, which means the following, that if I coincide these vertices with these vertices, they will be on top of one another. So the way we notate this is we're saying that triangle MON is congruent to triangle. So MON will be M, you are going to coincide which vertex. So M, you're going to coincide with 90 minus alpha. So the angle 90 minus alpha corresponds to vertex O. O corresponds to the angle alpha, so you're going to coincide it with vertex Q. And then N, you're going to coincide with vertex P. So we see that triangle MON is congruent to triangle OQP, which means that the distance from O to N is the same as the distance from Q to P, which we just worked out to be x units, which is root 24. So the distance from P to Q is root 24, and now we can answer the question by saying the area of E is going to be root 24 squared, which is 24, and that is the answer to this Olympiad problem. So the key thing is to realize that these two triangles at the bottom of square D are congruent, and that allows you to calculate the distance from P to Q to be root 24. Knowing the side length of square E, that allows you to work out the area of square E. Good.